Hiya, and welcome to theoretically the last video. We'll see how much we get through. The last video of this week. So in this video, we're talking about continuous distributions. So far this week, we've talked about discrete ones. So things where our numbers are integers, 0, 1, 2, 3, etc. But now we're going to look at, well, what happens if we're allowed a range of numbers like pi and 1/2 and 3/4, and like, so think of this as grades, right? You don't ever get, well, not always, you don't always get like 1 out of 5 or like 3 out of 7, right? You'll sometimes get some weird odd number because you might get partial credit or whatever. So what we're going to do is we're going to look at a continuous nature. So in discrete case, what we learned is how to handle expected value and standard deviation. And we're going to do the same thing for the continuous case as well. So like the thing we can kind of do is, like, for example, in the binomial, like the thing to kind of note with between discrete and continuous is with the, like, look at the binomial case, right? So if I look at the binomial distribution, this was drawn as like little bars. And basically the probability at any point was given by the area of this bar, right? And this was always some number. But when we looked at the normal distribution, what we saw is this was like, that was a bad graph, was something like this. And if I took the probability at any point, then the probability was 0, right? We said the probability at any point is 0. And so this is the problem that we're going to be having with continuous distributions, that the probability at any given point is always 0. So we can't actually just talk about probability at a point. We have to look at an area under some curve. So let's kind of go back and remember how the normal distribution was made. And basically what we had is we started off with some function, right? So we started off with some function. In normal distribution, what was this example? What was this? This was phi of x, which was 1 over, we'll just do the easy one, we'll do standard. We had this, right? We had x squared over 2 was the function we kind of had. And this is what gave us this bell curve, right? And so looking at this bell curve, we want to look at the area under the curve, right? This is basically what we had decided. So what we have is we have that if I want to look at the area here, what I have to do is really just take the area under the curve, which is just the integral, right? So here we would just take f of x dx. And this is basically how we're going to define continuous distributions. So as long as our function f of x is continuous, we can take this integral, and this is why this is basically called a continuous distribution, because we need this f of x to be continuous. And that's it. That gives us a continuous distribution. And the function f of x is called the probability density function. So it's not too hard to kind of see what this, like, where this kind of comes from, or like how this kind of works, especially since you should have already done integration and know the basic ideas of this. So basically we're only ever looking at the area under the curve. Note that we must always require that the area under the curve must be equal to 1, right? Or else it's not a distribution, because if I sum up everything, I need this to be equal to 1. So what is the sum of everything? This is just from minus infinity to infinity of my function. This needs to be equal to 1. If it's not equal to 1, then you don't have a distribution, and you can't do this. So the question now becomes, well, okay, how do we move all this terminology from the discrete case into the continuous case? In other words, what happens with the expected value? So in the discrete case, we had this, right? We did this kind of formula. Right? Now now that we think about integration, you should think of this as taking these columns, right? These are little columns, right? And what we're doing is we're shrinking these columns smaller and smaller and smaller. So really you should be thinking of Riemann sums. And if we're thinking about Riemann sums, eventually if we make them small enough, what do we get? We just get integration. So what we end up getting is, well, the expected value is, well, the sum of everything, aka the integral of everything. Remember, the integral sign is just a big S. So this is just S, and it's the German long S. So this is no longer around in German. Well, it is, but like they write it in a different way. So like, oh, sorry. This is the English long S. This no longer exists in English anymore. And actually, if you go back in older texts, you can look at this S, and it's kind of cool to see it. But this S no longer exists in English. It does exist in German, for example. So you see this for the long S in German. But anyway, like Gauss is actually spelled with the long S. But anyway, integration, summation, same thing. And we would just use our same function here as before. So we just do x times f of x dx. Well, okay, what happens when we try to do variance and we have to do x squared? Well, we'll just do the same thing. We'll just do x squared f of x dx. So it's not too bad. Like, it's same ideas. It's just now we're going to have to think of integration rather than summation. Well, okay, how about independence? Well, in the discrete case, what we have is this formula, right? So if two things are independent, we can multiply these out. But notice how we end up having a problem in this case. We can't have two variables that are independent because this is equal to 0 and this is equal to 0. So technically there is a way to define independence in continuous case, but we won't be covering that. We might later on in the year if we have time, but I doubt it. But for us, don't worry about it. Just know that I will sometimes tell you two continuous things are independent. And if that holds, then all the other rules of independence holds. In other words, for example, you can just multiply things, right? So this is one rule that we saw. If we have independent things, the expected values multiply. And obviously this needs to be that the expected values are not infinite in essence, right? So yeah, so this should be just like a little taster, a little bit of continuous distributions. We'll tackle these a lot more in the next week. This is just to kind of get you started on thinking about these things. The main idea, as you can kind of see, is that we take the same principles in discrete cases where we had a summation and we just change it to an integral, and that gives us the continuous distribution case. And that's basically it. So I will stop this video here, and I will see you all in the problem sessions, I guess. I hope you're having a good week, and I will see you then. Bye.